Okay, so let's continue our study of the sun. And let's talk about the source of the energy. Remember, all the energy is being created in the core of the sun and has to make its way out. But what is producing that energy? Well, it was a mystery for a long time. So let's think about it. So if you were going to figure out what is powering the sun, you might think, well, maybe it's on fire, right? Maybe it's just like a bunch of stuff that's burning. Well, in fact, if you take the chemical energy content, and that's what you need, so if you are burning wood, there's chemical energy in the wood that you are burning up to make fire and to give off that heat. If you took the total chemical energy content over the luminosity, so how much heat is being given off, you only get about 10,000 years of fuel, and that's nowhere near long enough. So that doesn't really work out. It's not really on fire. Okay, is it just contracting? Now, we haven't really talked about gravitational potential energy, but in fact, it's true that if you contract, you'll give off energy. So you're getting smaller, right? The gravitational potential energy is getting smaller, and that energy has to go somewhere, and that could go into heat. So people thought maybe it's just contracting. Maybe it's just contracting slowly, so we don't see it. Okay. But then you calculate how much gravitational potential energy does it have in total over how much it's giving off, and you only get a lifetime of about 25 million years. Again, not long enough. As we know, the Earth was formed 4.5 billion years ago, so the sun's about that same age. So the 25 million years doesn't cut it. And then people came by the idea of nuclear energy, and there was actually a physicist named Hans Bethe who figured this all out and figured it out in detail and proved that the sun's energy was coming from nuclear fusion. So if you take all the nuclear potential energy, so how much is there potentially in nuclear energy at the core, and divide by that luminosity, you get about 10 billion year lifetime, which is about what we think the sun has, about a 10 billion year lifetime. It's about halfway through its lifetime. So that is what we think powers the sun, and we have a lot of evidence now that this is true. All right, so let's figure out how that works. First, let's talk a little bit about the sort of weight of the upper layer. So imagine you're down at the core, and you've got all this weight of the rest of the sun pushing down on you. So here's that same idea here, right? This person's not feeling anything from anyone pushing down on him. This person's feeling the weight of this guy, but this guy, as you can see by his face, is taking the weight of these other two, right? So there's a bunch of weight from things above him pushing down on him. Same idea here with the pillows, right? There's a bunch of pillows stacked up, and as you get down here, it's the weight of all these other pillows that's compressing this bottom pillow. Same thing here with sort of a column of air, right? Okay, so the energy, so what, if it's true that the core is feeling all this pressure, what stops the sun from just collapsing in on itself under its own weight? Well, in fact, it's the radiation pressure. So what happens is the core is putting off light, and that light is actually pushing back on the material of the sun, kind of like that guy's arms holding up the two guys, and so that it doesn't collapse in on itself. And this balances that inward crush. Okay. Now, gravitational contraction provided the energy that heated the core as the sun was forming. So what happened is that it was just a ball of gas. There was no fusion in the core or anything, and it was contracting under its own gravity. And that heated everything up enough for fusion to get started. And we'll talk about why fusion needs the heat to start. But once fusion started, then the light that was produced by the fusion, the radiation, I'm going to go between light and radiation, think of it as the same thing, would push back and stop the contraction. Okay, that's once fusion started. So how does this nuclear fusion happen? Well, first we have to understand what fusion is. You've probably heard of fusion, like in movies like Back to the Future with Mr. Fusion, etc. But there's something else called fission, and fission is what we actually use in nuclear power plants today. And fission is where one nucleus splits into two smaller nuclei, and usually it's really big nuclei that do this splitting. And this kind of reaction, fission, is actually can become a chain reaction. So what happens here is this guy splits, and it also gives off something called neutrons, and those neutrons can cause other big atoms to split, and so on and so on. So you can get a chain reaction, which can be very dangerous. And when people were first messing around with fission, when they were inventing the first atomic bomb, people died because of this, from mistakes in handling this fissionable material. Fusion is quite different. Fusion is when two small nuclei stick together and become a whole new atom. So imagine two nuclei of hydrogen coming together and becoming a helium. Now it's a little more complicated than that, because we're gonna go over that. But this is something that we only recently have been able to do in the lab, and it's not a chain. So once you start it, you have to keep making it happen. It won't just happen on its own. And so if we could but it's very clean power. So you might know that fission power in nuclear power plants, while very safe in general actually, does produce nuclear waste. Whereas fusion, if we could get fusion power plants up, the only thing that it makes as waste product is water. So, and it's very safe because it can't make a chain reaction. So this would be great, and people are working very hard to make that happen. All right, so let's look at this in detail. First of all, to even start fusion, you have to get these things close together. So imagine you're taking two protons, right? So it's the nuclei of hydrogen atoms, and you're trying to get them close to each other, but they're both positively charged. And it's kind of like when you take, two magnets and you get them to a point where, remember, if you turn one around in a certain way, you get it so that it's really hard to bring them together. It's a similar thing, right? You have two charged particles, positively charged, and they do not want to get together. So you have to make them go very, very fast. So at low speeds, this repulsion, because they're both positively charged, they're never going to touch each other. They get sort of repulsed away from each other. But if you get them going fast enough, they'll slam into each other, get close enough for a whole different force called the strong force to bind them together. And this is the essence of fusion. But you have to get them going at high speeds. How do you do that? You make it very hot, right? Hot things are, the hot temperatures are when things are going very fast, right? So you make things go very, very fast, slam them together close enough to bind. All right. Well, in fact, the sun releases energy by fusing 4 hydrogen nuclei, that's represented by the 4 protons here, right, into 1 helium. So helium has 2 protons. 1 helium nucleus, it also has 2 neutrons. Okay, so how does that actually happen? So you get the 4 protons together into 1 helium, a helium-4 in fact, right, because it has 2 neutrons. Then you get energy. All right, well, this happens actually in steps. And the steps are where you have 2 protons and another 2 protons coming together, and they come together and they give off a proton and a neutron. And a neutrino, which is represented by this little gray dot, and we'll talk about neutrinos a little bit more, and a positron. A positron is actually an antiparticle. So you might have heard of antimatter. It's the antiparticle of electrons. So it's positively charged instead of negatively charged, but it's the same size and mass as an electron. It is an antiparticle. And so when these 2 protons fuse, they give off this positron, this neutrino, and a proton and a neutron. And that proton and a neutron is a deuterium nucleus, just a fancy way of saying a hydrogen with an extra neutron. Okay, so you have this extra nucleus here, this little deuterium. These things fly off, and then there's another step. In the other step, this deuterium nucleus fuses with another proton, and gives off this gamma ray, which is light, right? Very highly energetic light. And we get out of it, we get a helium-3 nucleus, 2 protons and a neutron. And then finally in step 3, these 2 things, 2 helium-3s, come together, give off 2 protons, and become this helium-4, which is the end of the process. Now, if we look, right, this is all steps in one, right? 4 protons come together, you get gamma rays, which is the light you need, you get a couple neutrinos, a couple positrons, and this helium-4. So when we do that, you come in with 4, you go out with a helium-4 nucleus, 2 gamma rays, 2 positrons, 2 neutrinos, And the total mass, if you add up the mass of all the products, is about 0.7% lower than the products that came in to the reaction. And that mass has been changed directly from mass to energy. Remember this equation? Energy equals mass times the speed of light squared. Okay, so if you took that 0.7% lower mass and you get this much energy from it, right? That's how you calculate it. So you're literally converting mass to energy in the sun. Okay, all right, so this process is actually quite, if you think about it, you're putting out all this energy, right, holding up all this material with these photons, the gamma ray photons, and this actually contributes to what we call the solar thermostat. So what does that mean? So let's take a look here. It's kind of like a thermostat in your apartment, right, or your house, where if it gets a little too cold, right, the heat turns on, it gets it back to where you set it. Gets a little too hot, the air conditioning turns on and puts it back to where you set it, right? You say you set it at 73 degrees or whatever. So this is a similar idea here. So let's say you had a slight rise in the core temperature. Okay, for some reason, got contracted a little bit, got a little hotter. Well, this would lead to an increase in the fusion rate, right? Because you are making the protons go even faster and letting them smash into each other and bind more. So you get a large increase in the fusion rate. That puts out more radiation, which raises the pressure, the core pressure, right? Because now you've got more radiation pushing. And that will cause the core to expand. And when things expand, they cool down. Okay? I don't know if you've ever used one of those cans of air. If you ever used a can of air, there are these little things you can buy. It's a can of air, looks like a spray paint can, and people use it for cleaning their keyboards because it pushes this high pressure air out, and you can blow all the dust off your keyboard or whatever you're doing, right? But if you've ever used one of those things, if you use it for a little bit, like 10 seconds, the can gets super cold because it's sort of compressed in there, and you're letting it out and you're letting it expand. Right, and so it gets very cool. It gets quite cold actually when you're holding it. And this is the same idea here. When things expand, they cool. And then the fusion rate goes down because things are cooling and you're back to normal. That's the thermostat idea, right? So it got a little too hot and then the air conditioning came on and cooled it back down. Similar thing here. Let's say we had a slight drop in the core temperature. Okay. This leads to a decrease in the fusion rate because things aren't moving so fast anymore. Then that lowers the core pressure. Less radiation is being produced by fusion, so lowers the core temperature, and the core collapses a little bit, contracts, and heats up. And for those of you who are, example of this is from, my favorite example is from scuba diving. If you've ever done scuba diving, I don't know how many of you have, but when they're filling the air in the air tanks that you use for scuba diving, they put them in a bath of water. Because when you're filling it, you're compressing the air and it gets quite hot. So they put them in a bath of water so it doesn't get too hot. So when you compress stuff, it gets hotter. And so that's how the solar temperature thermostat works. And it's this gravitation, sort of this equilibrium between collapsing and pushing back up on the stuff, stuff that's coming down on you from the core, from the rest of the sun. Okay, let's try a question. Pause your video and answer.